When working with domain events, another question that inevitably arises is how to deliver them physically to the subscribers. The answer depends on what type of physical isolation is used for bounded contexts. If the bounded contexts reside in a single process, then the delivery isn't actually a matter because the code in those bounded contexts share the computer memory. In the case of separate processes, the delivery goes via the network using some sort of a service bus. We will look at some of the techniques later in this module, but we will not dive deep into them in this course. However, I want to emphasize that just as physical isolation of bounded contexts is orthogonal to their logical isolation, physical delivery of domain events is not related to their logical counterpart. We can use whatever delivery technique we want, we can even persist the events and use them later in an event sourcing architecture. All such techniques use the same logical concept of domain event behind the scene. Before we move forward with domain events, let's build up the management bounded context and introduce persistence for it. This is how the table for the head office entity will look like. Once again, note that we are inlining the money value object here. Along with money, the table also contains the balance column. And here I added a row to that table so that we have some taste data to work with. The head office entity will need a functionality to change the balance, so we can add a change balance method to it and initialize the cache property. And now we need to map the domain class with the database table. Creating head office map, inheriting it from the class map base class. The mapping is quite straightforward, the ID field and the two properties, balance and cache. Next we need to add a repository for that aggregate, head office repository. It would also be empty because all required functionality resides in the base class. Good. And lastly, we need to think about how we will access the head office. Our stakeholders currently have only one head office, so it's a good idea to reflect it in our domain model. It doesn't make a lot of sense to always retrieve that single instance from the database. What we can do instead is we can employ the singleton design pattern and keep a reference to the head office instance during the entire application lifetime. We can implement the singleton pattern by adding a new class, head office instance. This class will hold the reference and our code will access it when needed instead of fetching it from the repository. Alright, we can make the class static and introduce a static property, instance. We know that the only head office in our domain model has the ID of 1, so we can specify it here as a constant. And finally, we need to add an init method, which would initialize the singleton by fetching the proper object from the database. We need to add a call to this method here in the initer class, so that it will be invoked on the application startup. You might wonder where in the Onion architecture this class resides. It plays the same role as a repository, so it resides in the second innermost layer on this diagram. It means that classes from this layer cannot access it. Only classes from the same layer or upper can work with this singleton. We didn't implement this functionality in the head office repository itself because it would violate the single responsibility principle. Repositories should fetch objects from the database and save it back. They shouldn't hold instances of anything. That's a task for another domain class. So now if we run this code, you can see the instance of the head office class was successfully loaded into memory. Alright, the head office entity is ready, and now we need to bind these two classes. So basically, when a user takes money, we need to change the balance of our head office by passing it the amount of money the ATM charged from the user. That's where domain events will help us. To handle domain events, we need to define an interface, iDomainEvent. This is a marker interface in a sense that its only purpose is to mark classes that represent domain events in our model. Another interface we need to introduce is iHandler. It has a type parameter which has a restriction. It has to be derived from iDomainEvent. This is an interface for all domain event handlers in our codebase. The type parameter t specifies what type of domain events it handles. The only method it must implement is handle. Alright, now we are ready to create a class for the event we discussed previously, BalanceChanged event. It should inherit from the iDomainEvent interface and it should contain the data about the balance change. To handle this event, we need to add a handler class, BalanceChangeEventHandler. It should implement the iHandler interface of type BalanceChangedEvent, which means that it should contain the handle method accepting the BalanceChangedEvent. To implement it, we need to create a repository, get the head office instance, change the balance using the data passed with the event, and save the office. This would be the handler implementation. Handlers are usually quite simple because what they often do is just delegate the actual work to other domain classes. You can think of event handlers as of domain services. Their roles are very similar. We will talk about domain services in more detail in the next module. Note that the event itself is defined in the ATM bounded context, whereas the handler for it in the management context. It is no coincidence because it reflects the actual relation between the bounded contexts. The ATM bounded context generates the event and the management bounded context consumes it and reacts accordingly. It also allows us to preserve the unidirectional relationship between them. So how can we glue the event and the event handler together? We will first implement the classic approach for this. After that, we will look at its drawbacks and then introduce a new one. Finally, we'll compare the two approaches to each other. Alright, to actually raise the events, we need to introduce a new class, domain events. It will be a static class. This is its content. Let's walk through it together. The idea behind this class is that it maintains two lists of handlers, dynamic handlers and static handlers. Static handlers are handlers that we define as classes, just as we did with the BalanceChangedEvent handler. This code here scans the current assembly for all such handlers and gathers them into a single list. It determines whether or not a class is a handler by looking for the iHandler interface we defined previously. Dynamic handlers, on the other hand, are the handlers we add during the runtime with this register method. They are basically just delegates, which this class adds to the internal collection of delegates for a particular event type. You can see the class pre-creates a dictionary for those delegates. The key of that dictionary is the type of an event, and the value is the list of handlers we add in the runtime. Dynamic handlers are usually used in unit tests to check that the events are raised correctly. This method processes the actual events. It first goes through the dynamic handlers and checks all that suit the type of the event passed in. It invokes each handler in the list. After that, it goes through the static handlers and sees if there is any that implement the handler interface. If there is, the method instantiates a handler object and calls the handle method on it. So basically, whenever we need to raise an event, we call this static raise method of domain events class and it dispatches the event to all dynamic and static handlers registered. We need to add the init method to the initro class so that it is also called on the startup. Alright, let's see how can we actually use this class. Let's add a new test to the ATM specs named TakeMoney_raises an event. Here we will create an ATM, load some money into it and take that money. After that, we need to somehow check that the event was raised. How can we do that? This is where the register method will help us. We can register a new delegate which would save the raised event in a local variable, like this, and then verify that the event was actually raised by checking that it's not null and that it contains the correct amount of money in the delta property. The register method call throws an exception because the dynamic handlers collection is not initialized. I need to add a call to the init method to fix that. Good. Now you can see the test fails on this line, which means the BalanceChangedEvent wasn't actually raised. To implement the required functionality, I should call the domain events raised method in the TakeMoney method and pass it a new event, BalanceChangedEvent, with the amount of money with commission. The test is passing now, which means the event was successfully raised. The approach we employed in the previous demo works, but it has two major drawbacks. The first one is that it violates the isolation principle we discussed in the first module. Layers in the onion architecture should know only of themselves and the ones residing lower. They shouldn't depend on classes from outer layers. The ATM entity works with the domain events static class, which doesn't belong to the innermost layer of the onion architecture. Therefore, this implementation damages the isolation of the domain model. The lack of proper isolation results in several smells we can see in our codebase. One of them is this awkward delegate we have to define in the unit test in order to check that the event is raised. Another one is the list of dynamic handlers in the domain events class and the register method, which is used only in unit tests. Introducing code in the domain layer that is used in unit tests only is generally a bad practice. The second drawback is that such implementation doesn't fit into the notion of unit of work. This is best expressed with an example. Let's say that we start a business operation. It first executes a method which results in a domain event, employs some validations next, and finally saves everything into the database. The happy path in this case works fine. An event is produced, the subscribers successfully consume it, all validations pass, and all data is persisted. But we get a problem in case the validation fails and we need to terminate the operation. The problem is that the domain event is already raised and processed by the time the validation fails, and there is no easy way for us to roll back the changes made. This is why this implementation doesn't fit the notion of unit of work. The act of processing an event occurs before we commit on producing that event. Another example of this problem is multiple mutations. We could change the balance of an ATM for several times during a single business transaction, and each time we do that, a new event is raised and processed. A better option would be to create only one final event with the overall change and raise it instead. And it's really hard to implement this option using the code from the previous demo. These shortcomings make the solution we introduced unreliable for any more or less complex situation. I brought it here just to make you aware of it, because many programmers still employ this approach when we work with domain events.